Welcome back, everyone, to this afternoon session of ML4HPC. Babak Al-Safi from KFL. And it's a great pleasure to invite Gunter Roeth, who is a solution architect at NVIDIA. He's in NVIDIA since 2014. Before that, he worked at Cray, HP, Sun Microsystems, and recently at VOLTA. He did a master's in geophysics and a PhD in seismology, looking at the application of AI and neural nets on geophysics. The front of this recording is cut because we had difficulty recording the first couple of slides. Gunter will start on the third slide after the cover. So.
In AI and is still going on today when you look at all the wonderful applications that exist today. Okay, and so we need something new, and why not combine HPC and AI to create a new revolution that can now, so with these AI tools, really go into the HPC applications and to try then to get them much better scaling than, for example, the only double performance or something like this. What we would really need a factor of 1,000 or so to go to the exascale. So data, yes, we already have a lot of data. This is why the deep learning was so successful. The possibility to train the networks on big number of examples, for example, on all these pictures and computer vision processes or programs, the possibility to have a lot of examples of text, a lot of examples of translations, and so on and so on. So in all these domains, the networks benefit a lot, and only in this context can really beat the traditional machine learning algorithms if they are trained with a lot of data. Okay, so this was something that you see always more and more often see, that for all this processing and the training successfully, when you want to do it successfully, you need a lot of data. And so here now, yeah, we have ranges from gigabyte to terabyte, petabyte, up to zettabyte, of course. And I come more from the geophysics domain. And so big data is usual in the geophysical domain, and so geophysics has a lot of, or traditionally already a lot of data, but of course much less than, for example, what you can imagine for these connected vehicles that come up in the zettabyte range, when you have all the sensors in the different cars, and then they will communicate. And then you have to centralize this somehow, and so on and so on. So this is really perspectives of massive growth and accumulation of data and processing of data that is gigantic. And and I already mentioned in geophysics, we have a lot of data, but we are not the only one. So for example, when you look at the Large Hadron Collider, the LHC in Geneva, they have, they are also easily in the hundreds of petabyte range, what they generate a day, what they have to process a day, and so on and so on. The Johns Hopkins Turbulence Database is all done with direct numerical simulation, so DNS studies can be queried from here. And then, of course, at the end, we have the square kilometer array. This is still needs to be implemented. But of course, on the paper, this one looks really amazing how much data, again, in the petabyte range, you will have to ship around the Earth to get finally then a good reconstructed image of the satellites or whatever you want to whatever you want to record. Okay, so the SKA will be also a huge data producer. And just one more word here to the LHC. So LHC, of course, are undergoing continuously upgrades. So they get a better detector, they get a longer ring, more or less, and so on and so on. And in this case, of course, you will again double or quadruple and scale, produce more and more, even more data. Okay, but this is a known problem today. Okay, so now I already mentioned the artificial neural network, so the artificial intelligence. So what is one of their successes? Okay, the success of neural networks is that at least on the paper they can map from any input space to any output space. Okay, so you can think of an input space, for example, an image with a cat and an image with a dog, and then an output space classification: is this a cat, is this a dog, and so on and so on. So neural networks are able to, when they presented a lot of data, to learn this input-output mapping. Okay, so always map an input space to an output space. There is also some proof that the neural networks are universal approximators. So why not try to use them in HPC? Why not here, for example, we see a supernova simulation. So why not train them to run the supernova simulation? We have a lot of these simulation codes. We have fluid dynamic codes. We have wave. We have geophysics code, and so on and so on. So wave processing, wave propagation, and so on. So why not run a simulation and train a network to exactly say the parameters of the simulation. Okay, so for example, here, for galaxy formation, this is an n-body problem. So we would find the original position of the bodies in the beginning and something like this. Okay, or for example, in geophysics, wave propagation. So find the underlying. So show me a seismogram and then retrieve the underlying Earth model velocities and something like this. Okay, so we can create in HPC. We are able to create a lot of these simulations. Okay, so now we can train the network to do the simulation for us by showing them a lot of data, and then we can do, of course, some regression if we want, and then finally, once the network is trained, the good thing is, once they are trained, so training is always a very long and difficult process, but once they are trained, then you can run inference. And inference is very, very rapid. Okay, so inference is quasi instantaneous because you just have to run through the network once from your input to your output, and this is very, very fast. Okay. And also what you can see here is that with traditional simulation, so we are always bound to 64 or 32-bit. So very often, so we need double precision. And however, neural networks, when you train them, then you can already train them today on simple precision or half precision. This is possible. And once we come to the inference, then half precision is more, nearly everything you need, or you can even go down to integer rate or even less. Okay, so here you can see you can gain still additional computational power because then, of course, the place to store the network in integer rate is, of course, much less than it would be on, for example, in double precision. Okay, and so this is a little bit the idea on how we can now perhaps combine the AI workflow for HPC. And so in HPC, what we rely on is really 40 years or longer of all these fine-tuned algorithms and created have everybody or a lot of research groups have worked a lot in the details of the simulations and so on and so on. So there is a lot of work, and so this definitely has not to be thrown away. But now we have to combine it somehow intelligently with what the AI now is offering us or is promising us. Okay, so when we combine them cleverly, then the HPC algorithms will benefit. Okay, and then once they will benefit, or what yeah, we have a couple of areas that are of course a little bit predominant today. So one, of course, is I already mentioned, all the climate simulation. Of course, we have the all the universe and so on and so on. So there, and new medicaments and so on. And so all these domains will be highly beneficial to combine now these two methods. Here we see also a little bit listed on so we have on the left, we have where the artificial intelligence help to improve accuracy. And so here, for example, we get, for example, for the fusion experiment, the neutrinos ligand docking, so we get a much better ligand scoring, ligand score. And of course, the climate, all what concerns climate. And here, when we combine HPC and deep learning, we improve highly the accuracy of existing methods. Okay. And then, of course, we have new ways on how to implement this one here. And so, for example, here in the LIGO, so to detect the gravitational waves, we see here a black hole in front of us. This one's 5,000 times faster, and so on and so on. SLAC gravitational lenses, University of Canberra, the Bose-Einstein condensate, so coming to these ultra low temperatures, and so on. Okay, so here, every time when you combine these methods, for traditional methods and the new ones, then you get a huge acceleration compared to what you had before. And of course, here now, I have only mentioned the simulation part. Okay. So yes, so what else we could think of is the simulation part is also to perhaps try to run coarse simulations only, and then let them be refined by the artificial intelligence. So this is what always also done, for example, in images, so coarse to fine images, or even high, so very fine scaled images, and so on. So all this is possible. Okay, and so this is done for the simulation part. But you can also think of a lot of these tips in the pre-processing or in the post-processing. Okay, and the pre-processing, which are the most important control parameters, which are the parameters I will have to look for, and so on and so on. You can also, for example, augment and distribute input data, and so on. And then at the end, you can have a post-processing. In post-processing, it is easy to understand whenever you have something visual. Okay, so whenever you can get visualization done. Okay, and this helps, of course, the post-processing enormously. And if you directly see your result, if you directly see what is going on, okay, and we will see also how deep learning then can help here to speed up the entire processing chain, and that you can run it then in real time or near real time, and that you can directly interact with it on the via visualization. Okay, so this is a great progress. Okay, so the AI, what the shape of AI supercomputing is what I already mentioned earlier. So this is the Summit supercomputer at Oak Ridge National Labs that was installed 2 years ago. And so it has 122 petaflops for HPC with 64 bits, okay, normal double precision. And however, when you compute all resources that are on the machine, because the VOLTA GPUs on the machine have special processing units that are called tensor cores, okay? And when you compute the additional power of or when you compute the overall power of the machine, you come to 3 exaflops, okay? And then of course we have here one application that comes from the genomics that is doing some genomical simulation. And so it tries to really combine the connection from the genes to the disease, okay? So, and so they adapted their algorithm to run on Summit, and using now the tensor cores, using the whole machine. And here you can then see that you come into the exascale range, okay? You are really you're really touching the exaflop arena here with these simulations, okay? So this is so here we have on these examples we have it. Well, we see that it's possible to get an exaflop today, and perhaps this can inspire you for some of your further research or something like this. And here also what we can see now is that, as already mentioned before, the linear scaling is not longer promised from the hardware. And so, but what we can do here is we can just hope on the on this AI and HPC revolution to give us whatever we need by 2025 or whenever we have the first exascales machines. Okay, so the 10,000x will not only come from the hardware, or will of course help by the hardware, but then will be largely made possible also by the software, by the algorithms, and so on and so on. And so now let me show a couple of examples here. So on the left you see the traditional computational science problems, turbulent flow. I already mentioned DNS, the n-body simulation, and so on and so on. So these are traditional computational science problems. In the middle, we see the couple of big successes in data science. So, for example, we see the Go game that was solved now, and so the Go champion of the world is actually a neural network trained by Google DeepMind, and so on and so on. And so you can look up these ones, but will get the slides later anyway. But you can look it up on GPU, on GTC on demand. Okay, so GTC on demand is a fantastic site where all the GTC speaker conference presentations and so on are archived. Okay, so you can just look at the GTC on demand webpage site and find this talk that was given at the GTC last year. Okay, so now let me come back to this computational science. So to this problem here. So here ANOMALY is a network that is trained to compute the quantum chemistry simulations. Okay, and so to compute all these energy surfaces of the molecules and so on and so on. And so normally when you do these ones here, you would use DFT. So this is density function theory, and the DFT is very, very expensive to compute. Okay, and so here with this approach, they will train a network based on trained from this DFT data. So they will generate a lot of chemical components and so on, and you will train the network. And then the network we can run. And again, it is it's a huge speed up, because once the network is trained, it runs in microseconds. And however, when you have these DFT methods, you always have to wait a couple of minutes before you get your results. and here we see a little bit the different on how it was trained. So 20 million DFT data points have been used to train the networks. They have molecules from 1 to 8 atoms from the GDB database. And on the bottom right, you see a couple of molecules, how they would look like. So you have very simple molecules up to really also some really complex structures. Okay, so all this is now learned by the neural network. And then you see on the graph above, the accuracy of the neural network is very, very comparable to what you get with DFT. Okay, so, but of course, running at a fraction of time. Okay. So this is one possibility today. And then we have the computational mechanics. And here, for example, this is the one that I mentioned earlier. So here, for example, we have structure-borne noise. This is a small startup here, an example from a small startup working for Volkswagen. And so here, what they have done, they have accelerated. So all this structure-borne noise, they have trained a network. And when you run this one here now with the network, you run at real time. So this allows you to do visualization of the structure-borne noise of the structure, of the motor or of the car parts, and but you can run it in real time. Okay, so you can actually see directly and interact, see this was perhaps not a good idea, and so on and so on. Okay, so this one here is really working very well. Also, we have this one here, and this one here is accelerating Eulerian fluid simulation with convolutional networks. And this one here is a little bit different from the approach, because here what you're doing is, so here when you take the Euler equation, and then you have to do, so step 7 is the pressure projection to calculate UT. Okay, and then you will have to solve the Poisson equation and to find PT, so the pressure. Okay, and this step 8 is very, very computationally expensive. Okay, and so what they have done here is they have taken a network and they have trained a network, or to be included, that computes really the pressure projection. Okay, and that is the most computation intensive part of this program. And by doing the pressure projection, they can then get all these very, very good results and much, much faster than this traditional numerical processing. And here is a film. I hope you see it now. And you can see now that there's normal smoke propagation. The smoke is always very difficult. And then they have a couple of and they also have Arc de Triomphe. So you see the smoke propagation around. And you can compare it now with MantaFlow, and and you will see that there's not much of a difference. Okay, so the MantaFlow simulation is here. And again, compared to MantaFlow. Okay, so yeah, and this is how it looks like, and this is how they can speed it up. Okay, and this one, okay, and so now from this one here, from the PDE solution, here. Yes,
I have a question, Gunter.
Yes, yeah.
How much was the neural net faster in this case?
I don't know. I think it was from days to, I don't know. I will have to reread in the article. Yeah.
It's usually several orders of magnitude, basically.
Yes, it is. Yes, yeah. and but I don't think that they can get it in real time now. But it was much faster, because this step is really difficult to compute in. It's always the Poisson equation is really difficult to be solved. Yeah. Okay. And yeah, so here from this idea, there are even more ideas on working on these now partial differential equations. And and this is here, for example, a presentation or a work that we presented now at in Denver at Supercomputing 19 in Denver. And this is SIMRIS. And so SIMRIS is a physics-informed neural network. Okay. And so we will see, yeah. And here, for example, you will see what I mean by this physics-informed neural network. Okay. Normally what you do is, I said, you can train your network for example, with, for example, velocity images, okay, and then try to have always these images, and then you hope that the network will learn how the how for example the how the fluid flow will propagate. Okay. However, this becomes very difficult because the network does not have any physical information. Okay. So the idea here is not to have it to be trained on the big data side. So a lot of images. So I have a lot of images of fluid dynamics. So let me train my network, but also to make the network be much more sharper to recognize what is going on by learning him or showing him the physical, the physics of the problem. Okay, and this one was, for example, presented in a talk, for example, about the lake temperature modeling, and
there's a noise somewhere.
Yeah. This is okay. Yeah.
Okay, there we go.
So this was presented in a lake temperature modeling, okay? And so here, for example, in lake temperature modeling, you will not allow certain temperature profiles and so on and so on. And when you do this, you get, of course, much finer or much better results, okay? Because you exclude a lot of possibilities for the network to give wrong answers, okay? And here, for example, and then these networks are called physics-informed networks, okay, because they know the physics. Okay, and so here, for example, on the top, we see a normal equation here to do this vortex-induced vibration problem. This is the flow past the cylinder, and the cylinder is moving a little bit here. And so here you see that this is just a normal equation depending on time and the derivatives in time. And so what you can do is to train first a model by having a lot of these displacements that you have for training, and then have some kind of additional network that will learn about the really the physics part. Okay, so you split your network in two parts. Okay, and here on and then when you look down, we have the incompressible Navier-Stokes equation. Okay, so in this case, what we see here is that of course we have now a two-dimensional input on x, y, and t. And then, of course, we have pressure, the horizontal velocity, the vertical velocity, and so on and so on. So we have all these parameters, okay? And so we can train, so this part here, and then we can really have here the Navier-Stokes equation with all the derivatives. And what we can do now is we can think of the network that we see on the left side as a surrogate of the U function, okay? And so if we take this one here now, then we can compute the derivatives of this surrogate because we have it, and it is easy to do. when you're working with the frameworks, because you have automatic derivatives. Okay, so you can do automatic differentiation of all the networks, and so PyTorch and TensorFlow are all providing this. And in this case, it becomes more really easy, let's say, more or less easy to have an additional network that is then correcting a little bit what you would get from the original data train network only, and have it on some corrections that will only allow the physical solutions. Okay. And here on the right, you can see yet another scheme. So what we see here on the left side is a normal network, depending on weights and biases. And as I mentioned already, so this will actually simulate U, be a surrogate of U, and then U has to be as much, or the computed U here has to be as much as possible to the desired U. And this one is then explained, expressed in the first part of the misfit. And then you have also a second part of the misfit function that is about the physical residuals. Okay, so this is how you train them. And so, for example, when you look at the first one that is only trained now on data, so no physical knowledge, what you see is this one here. So here we trained it on slice-wise data, and you see on the left we see a little bit our training set. The training set is some random, organized but still connected features or bodies, or I don't know how you can forms, I would say, yeah. And so you take this one for training, and so to compute the true velocity. And then, so all this is only on velocity and pressure. Okay, so only velocity and pressure. Training is going well so far, so you will converge to something. However, when you run it on inference, and then you look at a little bit at what you would be interested. So, for example, all these two different car shapes. And of course, these two car shapes have not been included in the training set, so the neural network could not learn it. And here, when you look at the right-hand side, so you see that there is some difference in velocity. And well, for the truck above, it is still okay, more or less okay. However, the pressure is not well known, though there's quite some pressure error. And then, of course, when you look down here for what looks more like a car, all the turbulences then from the roof on the back to the car. And so they are not learned, okay? And this is also a little bit normal because they are not in the training set. So the neural network will not be able to learn it, okay? And so this is a little bit the conclusion here. And however, what we can do now is to use these physics-informed networks. And so here, but as I already said, but now we will train it here from a point cloud for 3D geometries. This works well. We have seen this one. And we will construct a network. Where is it? No. Okay, and we will construct, sorry, I was looking for a slide. That is missing. Okay, so here, so we are using the 3D geometry point cloud. And of course, we can also run training then, of course, on the tensor course and get it faster done. And so what we will do here is, of course, the complex geometries. We will get really a network that respects physics and so on. And after training, so for example, you can see now here the just a 2D lit-driven cavities, SimNet versus OpenFOAM. So OpenFOAM is from ANSYS, and you see that the network is perfectly learned, that there's no difference in U or V. And so, and you can take any test that you want, it will always be very, very good and compared to traditional solvers and traditional software. Okay, so this is very promising. And then, of course, we wanted to apply it here on a heat sink. And the heat sink, so here again, the numerical simulation are then, of course, with IcePack from ANSYS, and but I don't show the slides, but the numerical simulations are very, very close to what you would also get with IcePack. And so now let us look a little bit about the heatsink problem. So the heatsink is really, you will have to get the equation, the Navier-Stokes, of course, the turbulent Navier-Stokes equation for fluid flow. And of course, you will have to have some heat transfer to fluid and some heat transfer in solids, okay? Because the chip is actually heating, and the chip will then propagate to the fin, and then from the fin you will get this air ventilation going on that is taking up the heat, and so the processor can stay cool enough, okay? And so this is a little bit the characteristics of this network. So we have all these equations to respect, and we'll then construct our physics-informed network. And now up. And now this is a film that is actually showing this one now in action, and also how SimNet would look like. I hope you can hear it.
So what we're showing here is an application of SimNet, which is a framework for doing physics-informed neural networks on GPUs. And the use case we're using it for here is to accelerate the design space exploration of a heat sink, which involves solving a coupled fluid flow and heat transport problem. You've got a heat source in this chip component on the board here, and we've got a heat sink design on top of it that we want to evaluate over a number of different conditions of pressure drop and heat in the chip. And what we're going to do is we're going to search over a variety of different configurations of this heat sink. In this case here, we've taken two of the parameters for the fin height, the center fin and the outer fins, and varied those over a number of different conditions. And so the methodology here is that we've taken a volume of fluid and the metal and all of the materials that are the heat sink and the surrounding air, and modeled them and the boundary conditions of the pressure drop coming in as a point cloud. So about 3.3 million points. And so the training phase here of the neural network is training a neural network on all those points in space and the various physical parameters at the boundary conditions on those points, temperature, velocity, pressure, material properties like heat transport or the viscosity of the fluid. And then training a neural network that maps those onto a loss function governed by the partial differential equations of Navier-Stokes for fluid flow and heat transport. And so what you end up with is a neural network that encodes all of the physically plausible scenarios governed by those partial differential equations derived from the various different configurations that we're exploring. And once you're done training the network, it takes about 4 days on a single DGX1, you end up with a neural network that you can evaluate in any one of those configurations in a matter of seconds on that same system. And so it allows us to, in this case, explore about 2,500 different scenarios. Here we're visualizing a subset of those so that we can see the two surfaces here in the window on the left, which is a surface in blue, which is the pressure drop over the variation between the center fin and the edge fin, and in red, the temperature drop, or the temperature max at the chip in the center. And so what we're looking for in this optimization problem is a condition where we've got a minimum temperature for the Tmax, while it's underneath this gray bar here, this gray plane here, which is the maximum pressure drop that our cooling system can provide. And what we ended up finding was that the optimal configuration was not actually a completely rectangular block here. We found that at this 15 pascals pressure drop, the optimal Tmax was 93.7 here. If you go any other configuration, the temperature is going to go up or the pressure drop is going to go up. And you can see here that you've got a slight peaking to the roof here, like a roof line on the heatsink. And kind of intuitively, that's because the heat is actually generated here in the center, where the chip is, and so having the surface area of the heatsink, more material there right over where the heat's generated is going to have more impact than material that's here on the outside that's further away from where the core of the heat's generated. So here we're visualizing the flow that's been simulated with flow lines that follow the geometry and the pressure, and we can actually use those to inform a real-time visualization of the transient flow visualized here with the colored smoke, where the color of the smoke is corresponding to the velocity of the fluid, and green here is slow and blue and purple is fast. And so you can see here that there's a slow flow through the core of the heatsink where it speeds up here and then slows down the core heatsink, but then there's this very fast flow that comes over the top that picks up and pulls it out and follows the streamlines down the back. This is something that we're using internally at NVIDIA to help model our heat sinks and do design space optimization, and we expect to have a paper describing the core of the physics-informed neural network technology out soon. That's right, so here these are non-optimal configurations. So here you can see temperature drop is below 15 pascals, but the temperature has gone quite a bit higher, 94 degrees. And here you've got a very low temperature, but you've got a really high pressure drop. And you can see that you've got a lot of, let me turn off the, so you see the low temperature here, not a big red spot here, a lot of heat transported out the back here. It's all green in the air behind, but you see you've got this really sharp pressure drop. The colors on the flow lines are the pressure. And so you're going from this yellow, orange, red to blue, and this really sharp pressure drop can create turbulence, not so good. The other end of things, you can go to a, really high temperature, low pressure drop, so the flow lines are all kind of the same color that's kind of flowing through, but you've just got this immense amount of heat build up here on the heatsink and that nice big red spot under there. So again, the optimal configuration we found was this one here.
Okay, so I hope everybody could hear it and enjoyed the work that we have done here. And as already mentioned, so earth science is of course some field, and here, for example, we can look at them at, for example, hurricane classification or finding the origins of hurricanes. So hurricanes also create a lot of nuisance these days. And so wouldn't it be cool if we can find a hurricane soon enough, and if we can also try to predict the trajectory and when it will come, and so on and so on. And so here, for example, this one is a work that was done, and on this on a database of all the historic cyclones. And so we trained a network to find the origin of the cyclone, detecting whether or not this one is a hurricane or not, and then of course also trying to predict the trajectory of this one. Yeah, okay. And the detection accuracy is really nearly 100% now. Okay. And so this is one idea here now for the climate science. Another idea is also what in all the weather codes, you had the rapid radiation transfer model, and this is then in the climate models. And this one is again the most computing time, or a lot of computing time is spent, and you can replace it within your networks and win all these computational time and to get it done much faster, and they're also at the same precision as the classical solvers. And of course, we have the computational physics, and here, for example, I already mentioned the LHC, and so what they have done here is at the CMS. So they have a simulation possibility that is called Géant, and so in here now what they did is so Géant is 100 millions of lines of C++ code, okay, and so what you're interested in is these trajectory reconstruction, and so what you can do now is to train a network, and especially now where it is the most computation intensive is in the calorimeter, when it goes through the calorimeter, and and to do this kind of analysis and trajectory reconstruction in the calorimeter with the what they have trained now is a gun, okay, and so this one gives the Calo gun, and it is of course trained and compared with the with this full order simulation that they are able to do now here at CERN. And then of course we have the gravitational wave. So gravitational wave are recorded here in this LIGO facility. So this is the Alliance Laser Institute, and so what we'll be doing here is they try to find on the right hand side you see the signal that is recorded, okay, and so this is actually the what you observe, and we have it from two different locations. So one is from Hanford, the other one from Livingston. Now you will have to find in this signal the true signal of a gravitational wave, and so here what they have done with the neural network. So they have trained a neural network to say yes or no, this this observed data contains a gravitational wave or not. Okay, and so in this case, the network helped a lot here to find the first gravitational waves. And then of course we have the ghost particles or neutrinos. Okay, and here also what you can do is again you can train similar like we have done before with the LHC example. So we have Géant and Genie. So we can train full order models, and then we can generate the data sets to train the neutrino detectors. And when you normally and you have an improvement of detection accuracy that will go from 33%, or that will be increased, of course, by 33%, and then it goes up to 49%. Okay, so this is also now possible with these neural networks. And finally, also what you have is these the ITER, and ITER is all the fusion energy, clean energy, and so on and so on. However, they are very, very susceptible to these to these disruptions. Okay, and when there is the smallest disruption, they can either implode or explode. They can stop working. They can damage the material. This is a very, very fine-tuned process, and so the real challenge is now to predict these when will they happen. Okay, so I come now to an end here. So all these examples have been, of course, done on our latest NVIDIA hardware, and with all the different softwares and so on and so on that we have underlying. Of course, is CUDA. The HPC guys will know CUDA, and so and then of course we have all the libraries the HPC libraries like GLASS and so on. And then of course we have also the deep learning libraries, the deep learning frameworks, and so on and so on. Okay, so.
All right.
All right.
Thank you very much. Should we go to questions? We have a few minutes.
Yes, sir. Yeah.
Okay.
Yes, of course, yeah.
I have a question, but I think I don't have the option to raise my hand. So
Okay. Go ahead.
No problem. Yeah, yeah.
Okay. So thank you for the talk.
Mm-hmm.
If we have a neural network equivalent of a simulation, does this also mean that we can have a platform independent implementation of these simulations? Because if I have a neural network equivalent, that means I can run it on any hardware accelerator, like either GPU, FPGA, or TPU, without any low-level implementation. Is that correct? Do you agree?
Yes. I highly agree with this one. Yes, of course, yeah. But of course you must also But today the frameworks must be also available on your proposed platform. Okay. And and normally this is the case. I mean, when you look at, for example, all the robotics is the robotic operating system is very close to Linux, and so on and so on. So yes, I agree with this one. Yes, and also in NVIDIA at least we have CUDA everywhere. So from the smallest to the biggest card. Every card can run CUDA, every card can run the frameworks, every card can run everything. So it is a very universal approach, yes.
Thank you.
Okay. One last question from Mario.
Yeah.
I actually, can you guys hear me?
Yes.
Yeah.
Okay, good. My name is Mario, I'm a PhD student at the PFL. I actually have it's one question, but it's kind of convoluted. The first question I have is, so in the common case, because I see you seem to have two cases, one where the data comes from the simulators, and the other one where you train your networks based on data from sensors.
Yeah.
My first question is there one use case that is more common, that is you can say it's the common case, or is it like a mixed bag?
No, it is not yet any common case, or any all what I've presented today is research and research results. Okay, so deep learning is helping a lot in the different segments, and but all these are research projects. Okay, so for example, when you look at the fluid flow simulations, okay, I'm not a specialist in fluid flow, okay, but if you would be a specialist in fluid flow, then perhaps you would have other criteria to validate your flow. Okay, perhaps you are considering some Reynolds numbers or some geometrical configuration that is not respected, although it is not done yet in the examples that I have presented. Okay, and so on and so on. So. So all this is research, and so if you want to contribute to this research, I'm happy to set up a project with you. We have a lot of projects that are possible, and so for example, SimNet was one of them, and so on. So yes, yeah.
All right. Okay, we're running just a tad late, so
yeah. Okay.
Thank you very much, Gunter, for this interesting talk. This is exactly the kind of material we're interested in covering here, about how some of the HPC and simulation application are either entirely moving to machine learning, or they're just they have a few stages in simulation which will then be mapped to neural nets. So we should move on to the next talk. Thomas